We are going to talk about solving trigonometric equations.
Beautiful.
Doesn't that sound like fun?
It does.
All right, so let's, if I ask you to evaluate this, right? Evaluate the sine of pi over 3. I'm basically saying, okay, here's an angle, and I'm asking you to find the ratio of sides that is the sine, right?
Correct.
Opposite over hypotenuse, or your y value over your rotating arm, however you want to think about sine, all right? And we solve that by either looking at our unit circle or thinking about our unit circle or drawing a rotation of pi over 3, which of course is 60 degrees. If you're thinking of your unit circle, we should by now be familiar with these ratios and say, oh, the sine is square root of 3 over 2, right?
The y value.
The y value. Exactly right, when we're in a unit circle. So what happens if instead of asking you to evaluate an expression, what if instead I say solve something like this? So in other words, I'm asking for the angle or angles that result in a ratio of sides. It's sine, so it's going to be y over your rotating arm. What angle or angles make this true? That's all I'm looking for. When I'm solving a trig equation, I'm looking for the angles that make this true. How many angles do you think make this true? If I'm thinking about rotating.
One for sure.
One for sure.
Two.
Maybe two.
Three.
3, 4, 5, 6. Or I could go this way.
Is there infinite number?
There's an infinite number.
Oh, okay.
Isn't this fun? So we always, whenever we're solving these trig equations, because they are cyclical functions, right? We always have to give a domain. Solve such that theta, let's say, is greater than 0 or less than or equal to 2 pi. Am I still on the screen there?
Absolutely.
All right.
So that domain gives you the parameters for the angle you want.
Exactly right. Exactly right. So, hey, you can just look at your unit circle or look in your mind at your unit circle or draw a picture and say to yourself, when is the sine? I know, that never gets old for me. I think it gets old for my students. When is the sine positive? Well, as you said, the sine is associated with the y value. Sine is positive in the first quadrant and in the second quadrant because y is positive there. So I can think of rotating and terminating in my first quadrant, or rotating, terminating in my second quadrant. I can make two little reference triangles and think, okay, if I'm in my unit circle, I can call that square root of 3 over 2 and 1, and I think, oh, that's created by a 60-degree angle, or, in radian land, an angle of pi over 3 radians. Okay?
Fair.
So that's one of my solutions. My second solution, again, this is going to be another little 60-degree reference angle, or a pi over 3 radian reference angle. And if I think 180 degrees is pi radians, if I'm in thirds, I have 1/3, 2/3, 3/3, so I'm at 2/3 pi. That's how I think of it. I really think of the fractions 1/3, 2/3, 3/3. So 2/3 and 1/3 pi are my two solutions. That was fun.
That was.
So let's do a couple others. So what if I had something like, I don't know, 3 cosine of, and I'm going to switch to beta.
Is there any difference?
None whatsoever. They're just like x or y or any other variable. We just often use Greek letters. Since the Greeks did a lot with trigonometry, we kind of honor them by using their letters when we're solving trig equations. All right. Here we go. Oh my goodness. So I'm solving, so again, I'm looking for an angle that will make this equation true.
Got it.
Well, you know, I'm thinking I have to do a little algebra before I deal with my trigonometry. Sometimes students are really intimidated by that cosine of beta. So I say, hey, just substitute cosine of beta with x momentarily.
Because the cosine of beta, in the end of the day, is just a number, I believe?
Yeah,
Okay.
yeah, it's just a number.
Just a ratio, right?
So, exactly. So I could just replace that momentarily to help my brain, maybe, solve that. I'd say, oh, well, I could do that. I could subtract 3x from the other side and get x equals negative 1/2. Did I do that correctly?
Yes.
Yeah. So that's basically what you can do here. You can just realize, oh, I can just subtract 3 cosine beta. Of course, I could have brought things on the other side too, if I wanted to. And I'm left with 1 equals negative 2 times the cosine of beta. So the cosine of beta is negative 1/2. Hey, I'm back to where I was with the last problem now. Now I have a trig equation. I need to find the angles that will result in a ratio of sides of negative 1 to 2. Now cosine
is
x
value.
over your rotating arm. So in a unit circle, it's going to be just the x value, because my rotating arm we let equal 1. All right, so cosine is associated with x. So cosine is going to be negative when x is negative. So that's going to be in the second quadrant and the third quadrant. So I'm rotating and terminating in my second quadrant and in my third quadrant. And I know my cosine is negative 1/2. That means that little x value is negative 1/2, right?
Mm-hmm.
Oh, heck, I know this. I have my same ratio. Why did I do that? Oh, well, that's okay. My little reference angle is going to be pi over 3, or 60 degrees. And again, how do I know that? I know that because we have those 30, 60, 90 triangles memorized, I hope, right? So that's a little angle, a little reference angle of pi over 3. And my solutions now for beta will be 2 pi over 3. And let's see, we already did this. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3 will be the angle that's in the third quadrant.
Makes sense.
Are we okay? All right.
We have one more.
Let's do a quadratic trig equation.
Those scare me, Miss Stewart.
They do?
Yeah.
Oh, don't be scared. It's going to be just fine, I promise. All right. What should we go? You want to give me another Greek letter? I'm not very good at drawing many of them. Let's go back. Let's go back to theta.
That is the
And you know, I'm using 0 to 2 pi, but you can do lots of different domains. It could be.
Could you see an x in there?
Sure.
Could you see a y?
Sure. You can see any variable
so don't
at all.
be afraid of the variable.
No, yeah. In fact, let's do an x. Let's do an x.
That's allowed, right? That's
Sure.
allowed, yeah.
And I could go from negative pi to pi, or pi to 2 pi, right?
Mm-hmm.
All right, so let's try, let's do a sine again. I have to concentrate writing x's now. All right. Oh my God, oh wait, no, this is for another video. I want to keep the same trig function. That would have been solvable using a trig identity. But that's for our next video. Hey, this is a trig equation, but what kind of trig equation is it? If you see that,
Quadratic.
it's a quadratic. And just so you guys know, this notation means sine of x quantity squared.
Yes, that's key though.
That's just how we write it.
Yes.
It could be for tan or cosine or whatever. Okay, well, how do I solve quadratics? Lots of ways.
You factor it?
I could factor it.
Quadratic formula.
Quadratic formula.
Could
Complete the square. I don't, whole bunch
graph it, whatever.
whole bunch of ways. I'm thinking this is looking factorable.
I would agree.
So again, if this whole sine business, you can, if you want, just kind of replace it with some other variable and think, how would I factor this? Oh.
I think that's the factor.
That's going to work.
Yeah.
2a plus a is 3a. Okay, so if it's tricky for your brain with the, with the sine or the cosine or whatever, you can just temporarily replace it with another variable to see how the factoring is going to work. So this is going to be 2 sine of x times the sine of x. Factors of 1, 1 and 1, plus and plus. Of course, when you have two things multiplied to equal 0, that means one of them or both of them equals 0. That little trick only works when you have 0 over there, of course.
Of course.
It's the cool property of 0.
I think we're going to end up right where we were starting, aren't we?
We are! Look! Sine of x equals -1/2. Sine of x equals -1. Now I have two little individual trig equations to solve. All right, let's do each one. So sine of x is -1. Do you have me over here?
Oh, yeah.
Okay.
You're good right there.
So let's see. Sine is negative. Sine is associated with y, so this can be negative in the third quadrant and the fourth quadrant. Okay? And my y values are going to be -1/2. Gosh, I'm just stuck on this 30, 60, 90 triangle.
Well, there's only really
I know.
couple options,
That or
so-
45,
right.
45. So that means this little angle here is a 30-degree angle, which in radian land is pi over 6. Okay? Okay, so here I go. 1 pi over 6, 2 pi, 3 pi over 6, 4, 5, 6 pi over 6. One more is going to be 7 pi over 6. And rather than keep going, I'm going to go all the way. This is 2 pi radians, which is in sixths. It's going to be 12 pi over 6.
Yep.
Minus 1 is going to be 11 pi over 6. Does that make sense?
It does.
Okay, so I have two solutions so far for my angle. Sine of x is -1. Well, this is interesting. So my y value has to be -1. In a unit circle, if my rotating arm is 1, then that's got to be on one of the axes, right?
Yes.
Here, sine is +1. Sine is 0. Sine is -1. So sine is going to be -1 when I'm going straight down. And that is 270 degrees. In radian land, that's, let's see, 1/2 pi over 2, 2/2, 3 pi over 2. So there I had 3 solutions.
And there's only one solution to that right part.
There's
correct?
only one solution
because it
over
ends
here.
up on an axis.
On an axis, yep. Exactly right. Now, of course, I could check these like I can check any equation just by putting each one of these back into the original. If I took the sine of 7 pi over 6 and squared it, multiplied it by 2, added it to 3 times the sine of 7 pi over 6, added 1, I would get 0. Same thing with all of these. One thing though, a lot of students say, hey, do I have to check them? Do I have to worry about extraneous solutions? And the answer is no, you don't. The only time you have to check for extraneous solutions for any equation is if your original equation has some limited domain. Like if you have a denominator or a square root or something where you have a restricted domain. That's the only time you have to worry about extraneous solutions. I mean, you can check your work to make sure you didn't make a mistake,
right.
But if you did everything correctly, the solutions you get will be solutions. Alrighty, thanks Mr. Shanley.
No problem, thank you.
I am on a